Good.
So, hello everyone, and welcome to the European Non-Associative Algebra seminar. I'm going to introduce the speaker of today, Bruno Vallette from Sorbonne Paris North University, France. And the title of his talk is Homotopy, Bialgebraic Structures in Geometry and Topology.
Exactly. Thank you very much for the invitation. Can you see the screen?
Yes.
Yes, good. Maybe I put it in. Oh, no, not like this. I want to
Yeah,
control
but
It's
it's
better.
okay.
Why? Because you see, I want to scroll.
Yeah, maybe that's better.
Because maybe it's better like this. Okay. So yeah. So the idea is to cover a new trend in the study of homotopy algebraic structures in topology, geometry. I could put more algebra, computer science, but let's be modest so far. I will mainly cover the content of this paper with Johan LERAY, and it is related to several and then many other papers. One by Koncevic, Takeda, and Vlasopoulos. You have the reference here. Can you see the pointer? Can you see?
Yes.
Good. And you have this other nice paper of Alexandre Quesnay. Okay. So, and I will mention a few others. Okay. So the idea is to start with state of the art, a infinity algebra. No. So what do we do? Let me start with a very basic observation structure, say. So now, if you want to detect topology of spaces, how do you do that? So from the beginning of the 20th century, algebraic topologists have tried to find finer and finer homotopy invariants of the homotopy type of a space. Okay. The first one, well, first, the most simple one, let's say, well, let's put it that way. One which is quite computable is the singular cohomology of a space. So say homology or cohomology of a space. This is rather computable because it forms the underlying space here is abelian groups, chain complex, graded vector spaces. That's quite okay. I mean, compared with homotopy groups, for instance. And okay, so what do we do? We have a chain complex, good, associated to our topological space X over some ring field whatsoever. Here, I mean, for what I'm going to say, I don't need field of characteristic 0. It's going to appear later on. This is a chain complex with a derivation, okay? And it has a product. Quite unfortunately for this seminar, it's associative, but there will be a limit at some point. So this is the cup product in cochains, okay? And since the differential is a derivation with respect to this cup product, well, it descends. The cup product descends to the cohomology level, okay? So the cohomology groups, they do form a graded associative algebra, okay? But for a bad reason. So many people like this theorem, I don't. It allows us to compute the cohomology groups of some spaces because it's associative, commutative. So, there are associative commutative algebras that we like, for instance, the free ones. So sometimes we try to compute these cohomology groups and we say, look, I have 3 generators and I consider the free algebra on 3 generators, and that's it. Okay. But doing this, we lose a lot of data. Okay, so now let's see how invariant are these constructions. So they do behave quite well. If we have 2 spaces which are homotopy equivalent, okay, then the associated cochain complex and cohomology groups are related. The first one by a quasi-iso, which means that it induces an isomorphism on the level of the cohomology groups. So this is quite cool. I mean, if the 2 spaces are homotopically the same, then the cohomology groups are isomorphic. And this is an isomorphism of differential graded or graded associative algebra for this guy. Okay. So now the idea, of course, is then to understand the homotopy theory of differential graded associative algebra up to these quasi-isomorphisms, so since they are invariant of the homotopy type. So what do we do? The idea is to create a new category, the category where objects are differential graded associative algebras, but we want to localize with respect to quasi-iso. I mean, quasi-isomorphisms, they are not invertible. So if we have a quasi-iso of the GA algebra, it does not imply that there is a quasi-iso in the other way around, which preserves the structure. So this is a big failure of the theory. So what do? So these guys are not necessarily invertible, so we force them to be invertible in a much bigger category. This is what this localization has been doing for us. It's a huge guy which behaves in a bizarre way. Okay, so actually, instead of having just arrows, we consider zigzag of arrows, where arrows going in the wrong direction can exist, but they have to be quasi-iso. Okay, so inverse of quasi-iso. Okay. Okay, so this is a way to keep this data into account. Okay. But in passing to cohomology groups, like I said, we lose a lot of homotopical data. So how can we understand this more efficiently? And how can we do, not to forget any algebra homotopical data, passing to cohomology? Okay, the singular cochains, it's a very infinite dimensional space. So no, we don't want to work with that. It's too complicated. On the other hand, the cohomology groups, they're very often finite dimensional. So we would rather, you see, so here the algebraic structure is simple, but this guy is, wow, amazingly big. This is usually easy, but this is not enough. So can we fatten the algebraic structure in order to accommodate the homotopy type? So yes, we can do that. And this is where we leave associative algebras. And now we finally have something which is not associative necessarily. This is these A infinity algebras introduced by Stasheff and then worked out by Kadeshvili in the 80s. So what is an A infinity algebra? The idea is to relax the associativity relation up to homotopy. Okay, so we start from a chain complex as before. We start from a binary product, so a guy with 2 inputs and 1 output. But we also have operations with 3 inputs, 4 inputs, 5 inputs, etc. So we have operations, multilinear operations, mu n, from A times n to A. But I like to depict like this. So I view this as corollas from top to bottom, with n inputs and 1 output. Okay, and the degree of that map is in -2 if you wish, but you can hide that under the rug. And what do we want these A infinity algebras to satisfy? Well, we want them, that's the derivative of this, so A has a differential, the tensor product of chain complex has a differential, and a mapping space of chain complex has a differential. So what does it mean to do D of an operation like this? It means we do D here, plus D here, plus D here, plus D here, plus D here, minus D here. It's the derivative of a map. Okay, and this is equal to all the possible ways to compose the former operations. Okay, so here you have an example. What is the derivative of mu3? Is the associator. Okay, so this has a purpose. Okay, sometimes the associator is not 0, but we control more or less it. It's not 0, but on the homology level, it is 0 because it is d of something. And this something, this mu3, measures the failure of mu2 to be equal to 0. Okay, so mu3 it measures the failure of the associativity. Mu4 measures the failure of mu3 to commute with mu2, etc., etc., ad libitum. Okay, so it's a coherent way to relax the associativity constraint up to homotopy. You can pack that. There is a deformation theoretical definition of A infinity algebra, or let's put the other way around. Let's say I want to do the deformation theory of A infinity algebra structures. Give me a space A, a chain complex A. Then this is nothing but a Moror-Cartan element in the DGD algebra structure on the Hochschild cochain complex. Okay, so you can do that, but I will not cover this today, but you can do. So you can have infinitesimal deformations, formal deformations, etc. I am more interested into this question now. Is that okay? Good. We knew associative algebras and they admit morphisms. Wow, so it's nicely behaved category. What about A infinity algebra? I mean, we can definitely consider maps of A infinity algebras that could be a map from A to B, which commutes with all the structural operations. Yes, but again, homotopically theoretical is a bad definition. Well, it's a definition, it's nothing bad. I mean, but it does not have the nice properties that we would like for morphisms. They do not behave well up to homotopy. So the idea is to define a notion of A infinity morphisms, which are what? You see, in the same spirit, and there is a conceptual reason for that that I'm hiding here. I can tell more if you need at some point. So what is an A infinity morphism? It's not just a map. A map would be an F1 that goes from A to B that commutes with everybody. No, we want something more flexible. So again, we take a collection of maps labeled by n, the number of inputs. So each map is going from A times n to B. So it eats A guys from A and produces a guy from B with a certain degree. Okay, and it should satisfy something like this. So what do you want to do? You want either first to do F, and somehow you have no choice. You have to put a full level of F, because here the inputs live in A. You need all the outputs to live in B. You see, not just one or two, all. Because here you want to apply the structure, the A infinity structure you have on B. So this is an operation which eats guys from B and outputs in B. So somehow you have no choice. And take all the possibilities of that up to some sign that I don't want to make explicit here. In the other way around, what you want to do the product and then F. And this is infinitesimal, if you see what I mean. I am not taking a full bunch of mu here. The degree will not match. You see, if you compute the degrees that I gave here, this left-hand side has the same degree than the right-hand side. If you put mu here, no, it doesn't work. This is the right degree. Again, there are several conceptual reasons for this nice definition. Okay, if your collections here is 0 except for F1, or let's say look at F1 here, okay? You put one F1 everywhere, you put F1 everywhere and then you do mu, and then you put one mu and one F1 here. But then what I've been hiding here is I've been hiding the differential. So this is actually D of F2, etc., etc. So, okay, so again, this is a derivation, if you wish, of the notion of strict morphism. Now you're lucky because if you have a collection of maps where you have F1 and then F2, etc. are 0, this is a strict map like I mentioned before. This is a chain map which commutes with all the structural operations. So we say that an F like this, when F1 is always a chain map. If this is a quasi-iso, we call that A infinity quasi-iso. So this is the good generalization of the notion of quasi-iso of associative algebras. Okay, and so we're going to see that these guys, they actually behave very well. So what can we do with these maps? First, there is very beautiful homotopy transfer theorem, first proved by Kadeshvili, and then it has a long history. Many people worked on it or found it again, etc. I don't want to mention all of them because I will forget a lot. So anyway, let me give you the idea. You take a chain complex. You can view that as a topological space. And you take another chain complex, which is a deformation retract. That is, you pass from that space to the other one by continuous deformations, okay? So this small guy embeds into this big guy, and you can project onto it up to homotopy, okay? So what you have to, if you have seen that before, good. If you have not, the music is, this is a big space. This is another space which has the same homotopy type. You get one from the other by continuous deformations. But what about if you take a certain associative or A infinity algebra structure here? Since you're going to modify the underlying space on which they act, you're going to screw everything. So for instance, if you start from an associative product here, how to define an associative product here? But you can take elements here, and come back, and it's not associative. So shall we stop here? No. Actually, what we can do, if we start from an associative structure on the big guy, we can define a coherent A infinity, and this is where the A infinity algebras make sense. Here we have an A infinity structure on H, such that IP extends, this is what I wrote before, this is what I wrote in yellow here, or orange, I don't know. So each time you start from an associative or even an A infinity structure, there exists a structure with transferred on H, and you can extend these maps that were just one map into collections of maps that do form A infinity quasi-iso, A infinity quasi-iso, A infinity homotopy. So you see, what you have to, one way to view this is that here you have a homotopical data, and here you have an algebraic structure. And a priori, they do not mix well. The idea to fill this square, okay, is to promote these data into the suitable algebraic category, okay? This is a homotopical picture in chain complexes. You want to promote it into a homotopical picture in the category of A infinity algebra. And this is how you do it. And A infinity algebras have this nice coherent property that you can do it, okay? If you work only with associative structures, quasi-iso of associative structures, it doesn't work, okay? Somehow it's the minimal setting where this works. Okay, bright point. It's not, you can prove that such structures exist. Maybe you might wish one day to compute them. Here is a nice explicit formula. Okay, so what is the shape of the transferred structure? You take the sum over all planar trees with n inputs, and what do? You take n guys in H. You apply I to come from H to A. Then you alternate a product in a contracting homotopy, a product, etc., etc. So I, product, H, product, H, product. And in the end, when you have just one guy remaining, you come back to H with P. Trust me, it works. Okay. So for example, if you take the example we had before, singular cochain complex, the cup product, you can look at the formula for nu2, which is the most stupid formula, and then you get the mu bar. But then the mu n are what's called the higher, well, these are representative of the higher Massey products. So when I wrote equal, please, there are a quotient mark here, okay. This is related to Massey product. These are the universal formulas for the higher Massey products, which detect something. Okay, so here, by doing this, there is no loss of homotopical data, meaning now if you give me mu, I can recover mu up to homotopy, okay? Which you could not do if you were just considering the cup bar. So you're rather happy. And you're also rather happy because now these A infinity morphisms, quasi-isomorphisms, sorry, they do what quasi-iso of associative algebras fail to do. If you have one from left to right, there exists one homotopy inverse in the other way around. Okay, so what does it mean, homotopy inverse? It means, for instance, that when you have a map like this, it induces a map from the homology groups of A to the homology groups of B, an iso. This guy produces the inverse iso on the level of homology, so it's well behaved on homology. And another bright point is that this Sol data, and you can tell me it's not a Sol data, this is a collection of maps. But this Sol data helps you understanding this weird category, this weird localized category, blah, blah, blah. Okay, so what I'm saying here is that if you have a zigzag of quasi-iso, okay, strict quasi-iso of associative algebras, say, okay. Now, you know, here you have one map in the wrong direction, say. You don't know, there's no chance that there exists a quasi-iso in the opposite direction. If you stay in the framework of quasi-isomorphisms of differential graded associative algebras, no. So if you have a zigzag with 10,000 maps, well, good luck. But when such a data exists, actually this data is equivalent to just one. Okay, it's a collection of maps, but just one direct A infinity quasi-isomorphism, okay? Why? Because this guy is a quasi-iso of associative algebra. You view the DG associative algebra as an A infinity algebra, and you invert the infinity morphism, okay? And then you compose them, right? This is exactly the idea that Kancevich used to prove the formality of Poisson manifold. Well, the deformation quantization of Poisson manifold, and it relies on certain formality statement. Okay, so this is a big tool. I mean, using this instead of that to study formality theorems is a great idea. Okay. Feel free if you have any questions, interrupt me. I hope we have time. Okay, and just to mention one great other and more recent application of this theory, there's a nice result by Campos, Robert Nikou, Petersen, and Viestra, that the structure I mentioned before here, there was a conjecture that it, after the work of Sullivan, that it detects the rational homotopy type of space. It does. It does. And the way you prove it is by using these guys. Okay. So this beautiful paper that just appeared in Acta Mathematica. Okay. So now this is say the old story. This is associative algebra up to homotopy, and you see the tools we use: infini-morphisms, homotopy transfer theorem, invertibility of infinity quasi-iso. Does this theory works only for associative algebra? No, it's a universal one. So let me try to motivate it, to motivate other type of algebraic structures. So, okay, we've been encoding the homotopy type of spaces, part of the homotopy type, the rational homotopy type. Okay. What if, say, now I have an oriented manifold, and there is something that I like in algebraic topology, which also allows me to do many computations, is the Poincaré duality. Okay. The Poincaré duality produces you a Tom class, which is an invariant bitensor in the cohomology groups. Okay, well, so I'm going to view this guy, the Tom class, as an operation with 0 input and 2 outputs. That is, I'm going to view this as a guy in A times 0, but A times 0 is my ground ring field, to A times 2. Okay, so this C, which is a commutative bitensor, I like to view it like that. So imagine you have 2 copies of A here, that's it, and it's commutative. Okay. And then you can look, okay, here, what's the compatibility with the cup product? Okay, it turns out that, and it was formalized by Tradler and Zenlayan 20 years ago, something like that, maybe 15. They call that a V algebra. A V algebra is an associative algebra, sorry, equipped with a certain bitensor that, if you compose the bitensor on the right here with a certain input, this is equal to that. Why not? This is very natural way to encode part of the Poincaré duality. So keep this in mind. This is called the V algebra. Okay. Now, if you look in non-commutative Poisson geometry, what kind of algebraic structure arise? Alors, let me recall what people do in classical, say, Poisson geometry. So, classical geometry, we consider the commutative algebra of smooth functions on a manifold. Okay, no problem. We have functions. We multiply the functions because they land in our ground ring field, and we multiply the upshot in the ground ring. Okay. Now, when we want to do Poisson geometry, we want to add more on the manifold, what do? We consider bivector fields that square to 0. Okay, the Scatten-Nirenoi bracket of pi with itself is equal to 0. Another way to formalize this, not in terms of bivector field, in terms of functions, this data produces a Lie bracket, okay, on the space of smooth functions. And you might ask, okay, what's the compatibility between this guy and this guy? Oh, turns out that one is a derivation with respect to the other. And this is called the Poisson algebra for obvious reasons, okay? So Poisson algebra is a chain complex, or just a space, so here it's a space, with a commutative product, a Lie bracket that satisfies some Leibniz relation. Okay. So this is for the classical theory. But then we might have non-commutative analogs of this. To understand what could be non-commutative geometrical analogs to classical analogs, there is a principle called the Kancevich-Rosenberg principle, which says that, okay, guys, in non-commutative geometry, you should replace the commutative algebra of smooth functions on a manifold by a generic associative algebra. And you should recover these notions by passing to the affine scheme of representations. Okay. Okay, so if you do that, okay, what should be here, what should be put here, that would give under this affine scheme of representation this data. And this was solved by Michel van den Berg. He said, look, here, what we should have, let's give the analog of this guy. So what is the analog of a square 0 bivector field? It's a non-commutative bivector field, okay, which satisfies a certain Mohr-Cartan equation. Okay, and then if you want to have an equivalent definition in terms of an algebraic structure, you ask that you need a double bracket. Why is it a double bracket? Because it eats two guys. and produces two guys, okay? It's an operation with two inputs and two outputs. So this is very non-associative. And then you look, what does this guy have to satisfy? And Van den Berg called that a double Poisson because it's a double bracket, okay? So you start from an associative algebra, so which is this non-commutative bit, plus this guy, okay? And you ask that your bracket here should be cyclic skew symmetric. That is, if you switch the two inputs, then you're going to switch the two outputs at the same time, producing a minus sign. Okay, so I have to view your guy in space and switching the sign. Well, it's not very surprising. I mean, this is the two output analog of the skew symmetry of a Lie bracket. What replaces or generalizes replaces the Jacobi relation? You have a double Jacobi relation. So you see, if your box here, they had one output, you would recover completely your Jacobi relation. So it's quite natural. And then what replaces the Leibniz relation? It's not a big problem. You ask that this guy here is a derivation with respect to that. So that when you evaluate on the right-hand side with a product, it should be equal to this plus that, okay? So this is a Leibniz relation, the compatibility relation between the double bracket and the associative product. And this definition does the job in non-commutative Poisson geometry. And now last, but not least, bialgebraic structures that arise naturally. So the first one was in topology, the second one is geometry. Here, if we look at what's going on in quantum algebra and discrete geometry, we can now look not at any manifold, but a Poisson Lie group. Okay, we look at functions on a Poisson Lie group. And then using this structure, what do we have? We see that this admits a Lie bracket and a Lie co-bracket. So that is an operation with two inputs, one output, an operation with one input and two outputs, okay, bracket and delta. And what do they satisfy? The two-cycle condition says, oh, you can do the co-bracket of a bracket. It should be the sum of all the possible ways to do things the other way around. Okay. Oh, here I'm doing first the co-bracket and then I'm bracketing. Okay. And since this, you see, this is skew symmetric and this is skew symmetric, you need to have this alternating four terms. Okay. At least for the symmetry or skew symmetry. Okay. Well, that's it. And big issue raised by Drinfeld was how to quantize this thing, okay? And when we quantize, the idea is to get a certain bialgebra. So here it's associative, co-associative with the classical Hopf relation. The Hopf relation says that your co-product is a morphism of algebra, okay? What does it mean? It means you take the product, do your guy, or do your guy, then do the product, okay? So this is a morphism of algebra from A to A times 2, equipped with the suitable product in A times 2. And this notion of bialgebra admits an infinitesimal version. Instead of asking that this guy is a morphism, you ask that it is a derivation, okay? So then this is going to produce this kind of thing, okay? So here, you ask that you have an associative product, and you ask that your co-product is a derivation with respect to that, okay? That is, you do the product and then that guy, or you do that guy first and then the product, or do that guy first and then the product. And this notion is not as celebrated as bialgebra or Hopf algebra, which is a bit sad because I think it's quite interesting. So it was first introduced by Johnny and Rota in combinatorics, and then further developed and studied by Marcelo Aguiar. So the definition is what? You take an associative product, a co-associative coproduct. Like I said, you want the coproduct to be a derivation with respect to the product, okay? But then there is an extra condition you can or not put, okay? So this is what is called an infinitesimal bialgebra, infinitesimal for this reason, okay? It turns out that many examples and for some conceptual reason, for the duality of properas whatsoever, you would like to ask for this further relation, okay? This further compatibility, okay? Which is a compatibility between first doing the coproduct, but not like this, okay? You see, keep in mind that these guys are not commutative, okay? So the way these graphs are written makes sense. I mean, this is not equal to that, for instance. Okay, so this is different from this composite. Okay, you may ask that the sum, alternative sum of these four guys is 0. Okay, and but then why is that good? For instance, you can say, oh, hey, I know how to create a Lie bracket from an associative product. I skew symmetrize it. I take this minus that, and it's a Lie bracket. Sure, you're right. So what can we do? We can take an infinitesimal bialgebra, skew symmetrize the product, skew symmetrize the coproduct. We get a Lie bracket and a Lie cobracket. Oh, does it form a Lie bialgebra? Does it satisfy these two cocycle conditions? No. No. Okay. But if you impose this balanced relation, it does. Okay. So it's one good reason, another good reason. And you can look in Marcelo Aguiar's paper. He's definitely using, and there's a nice idea in his paper, using this algebraic structure to compute the CD index of some polytopes, okay, and prove some nice properties for it. Voilà. So you have three structures here. So the three structures I'm gonna have in mind is this V algebra here. So associative product and a certain box, 0 input to output. A certain infinitesimal bialgebra structure, associative product and a map with one input to inputs. And this double Poisson thing, which is an associative product and a map with two inputs and two outputs. So you see 0 input, one input, and 2 inputs for this extra structure. Said like this, if you ask anyone, they would say, oh, there's no relation between these three guys. Somehow they're right. So let's have a very naive look at this. Okay, comparison. So there is this notion of V algebra. Okay, this extra structure has no input. It's a bitensor. It's a bitensor labeled by some A, if you wish. So it's a coproduct. And here we have this guy which receives two inputs and produces two outputs. Okay. So if we have a V algebra, okay, maybe we can create an infinitesimal balanced algebra because we could try to produce a coproduct by composing the product we have here with this guy here. We plug it here and it creates an operation with one input and two outputs. And because of the relation of V algebra, there is no choice. There's just a unique guy like this. Yes, but if you check, this guy is not a derivation. Oh, okay. Then similarly, we start from this data of an infinitesimal balanced bialgebra. Okay, so a product and a coproduct. Can we create a double bracket with that? We can try. We plug the product followed by the coproduct. It's not cyclic symmetric, so let us cyclically skew symmetrize it. Okay, yes, but it does not satisfy the Leibniz relation. So like this, the talk should be over. Okay, so if we stay to strict structures, there's no, well, I mean, of course, there is something stupid we can do, or almost stupid. We can say we put this equals to 0. Yes, a V algebra induces an infinitesimal balanced bialgebra. I mean, you keep just the associative structure, but the associative structure is not very interesting. Well, you want to take the other guy into account. Okay. Now, how can I say that? So if you stay here, you won't see much. So now the idea is what? The idea is to take some further perspective on that. It turns out that, there is a theory which is called operades, which is an operad is an algebraic object which encodes all the operations acting on certain type of algebraic structures. So, for instance, there is one operad which encodes commutative algebras, and one operad which encodes Lie algebras, one operad which encodes associative algebras. Yeah, but here, operad encodes operations with several inputs and one output. Okay? Yeah, but here, no, we have operations with several inputs and several outputs. So we need one more elaborate guy. In the literature, you have several. You can start with props that were defined by Adams and MacLean in the 60s. props are easily defined, but they do not have a causal duality theory so far. Let's say a nice homological homology theory. Bon, for those who know this, I'm going to use either dioperad and more likely properad. If you don't know what this is, no problem, listen to the music. There is a nice guy, a nice theory where everything works. It's called properad. And what is a properad? Is a well-defined algebraic object which encodes operations with multiple inputs and multiple outputs. Okay. So, for instance, there is one operad which encodes V properad, which encodes V algebras. One properad which encodes infinitesimal bialgebras. It is made up of what? This properad is made up of all the iterations of the product and the coproduct. So we have a lot of graphs with genus, etc. And the number of them that you have, or the dimension of that space, is exactly the number of generic operations that you have. Okay. Same thing for double Poisson. So exactly like I said before, now what you do on these spaces of operations, you can send this operation to that and vice versa. There's no problem. But now, if you have this kind of operation in this properad, what can you do? There's no space here, because here your operations have at least one input, so no way. And if you do this, you see, composing that with that does not work. So you just have to send it to zero. So again, I mean, there is nothing new what I'm saying here. I'm just saying that the remark we made before can be formalized in this full level of operations. But this level of operations will allow us to work in a more relaxed content. Okay, so the statement is this. The only trivial statement that, like I said, is that any double Poisson algebra carries a canonical infinitesimal balanced bialgebra where you put zero. Okay, bon, this is not... But if you allow yourself to work with homotopy versions, I'm going to develop that later on. This is the fourth part of the talk, the last one. So give me 5-10 minutes. I just want to give you what this allows you to do, and then I will make them explicit. Maybe I should have done things in the other way around, but anyway. Properads admit certain homological property theory called causal duality theory, which allows us to produce homotopy version of these structures. Okay, so in the very same way as we could do A infinity algebras from associative algebras, we can do homotopy V structures, homotopy infinitesimal bialgebras, and homotopy double Poisson bialgebras. Okay, we can accept that. And they are made up of a lot of operations, and we encode that inside a huge properad whatsoever. You know what? When you pass on this level, then the good notion of double Poisson up to homotopy, that Johan LERAY studied in his thesis, is nearly the same thing as homotopy infinitesimal bialgebra. There is a surjection of properad from this guy to that guy. Similarly, if you look at genus 0 V infinity structures that Kontsevich, Takeda, Vlasopoulos called pre-Calabi algebra, you have a surjection map to this. So you see, if you pass to these more flexible homotopy versions, yes, they satisfy a nice hierarchy. Okay, you have this structure. This is a slightly more general, more operation. This is again slightly more general. Wow. So this allows you to connect the topics I mentioned before: non-commutative Poisson geometry, combinatorics, quantum groups, and topology. Voilà. I don't think I want to do that. So if someone wants to see this, so you see there is a proof here. So how do you do that? So what I mean is that if you know what causal duality theory is, you already know what I'm going to say. If you don't, you're lost. So there is a technical way to do all of this, which is called causal duality theory, okay? Which will produce these versions for you. Let me just summarize one point, is that each time you start with a space of operations, let's say the properad, which encodes V structures. In this causal duality theory, there's the word duality. So what the first guy that you can do is compute the causal dual. So starting from a space of operations, you can compute a dual space of operations, which does not have the same number of operations and they do not satisfy the same thing. Okay? And on this dual space, you have more flexibility. So let me show you this. Yeah, that's it. Okay, so let's compute or accept it. what is the causal dual notion to V algebras. You keep the same guys, you keep the same type, the same type of operations. A guy with two inputs, one output, and a bitensor. The causal dual of the associativity relation is again the associativity relation. Cool. So this is an associative product. But now you see, and the causal dual of the V relation is the V relation. So V shriek is V. Right, that's it. Okay, you change nothing. If you want to see something a little bit new, you have to go to infinitesimal bialgebras. So what is the notion, which is causal dual to infinitesimal bialgebras? It is an associative, co-associative, product, coproduct, where you see here, you do not have the derivation relation. Previously, on infinitesimal bialgebras, we had that this was equal to that plus that. Here you have that they are equal. Okay, so before, in infinitesimal bialgebras, this was a derivation with respect to that. Now, this is a morphism of module. Okay, you consider A to be a module over itself with the product, and you ask that this guy is a morphism of module. So derivation, its causal dual becomes morphism of module. In the same way, the balanced relation, when you had the sum of these four guys, alternate sum of these four guys being equal to 0, here you ask that they're all equal. Okay, and then you ask some higher genus stuff. This is 0, this is 0. And what is the causal dual notion to Poisson, double Poisson algebras? Associative product by a double bracket, say, but now the double bracket, you see, does not satisfy the Jacobi relation. All the composite that appear in the double Jacobi relation, they are equal. It's not the sum of the three is equal to 0, they are equal. And similarly for the derivation relation, you can switch. You see, when the product is below, you put it above. It's not equal to the sum of two, etc. Voilà. Bon, so you can say, okay, good, you have this causal duality thing. What does this give me? It gives you more degrees of freedom. This is what Kenne found. It's a really nice point in his paper, brilliant point in his paper, is that now you do have genuine maps between these three guys. Okay. Now, when you have a double Poisson like this, yes, you can send the box to this guy, and yeah, it works. Then you can create a co-product. I forgot to put an output here. Okay. So then, and it works. So you see what failed, what was failing in the classical picture works on the dual picture. And since the dual picture encodes all the higher operations of the homotopy bialgebras, then it explains why you have this. So when you pass to causal dual world, life is beautiful, or to homotopy world. You have more degree of freedom, etc. Now, several remarks. This is about construction. Here I've just been using construction. There is another thing which is called the causal dual property, which is a homological property, which tells you that infinity versions are somehow well behaved. I'm cutting very short here. So what about this causal dual property? Poirier and Treadler proved that the genus 0 properad, which is a dioperad, so if you consider only graphs of genus 0, yes, they behave well, they are causal, okay? And what they call V infinity algebra is exactly the it goes the other way around. Treadler and Allen defined the notion of the infinity algebra, which then were considered by Kontsevich Vlasopoulos under the name pre-Calabi algebra, and Poiré Treadler showed that this is the notion which appears in the causal duality of the V algebra. Voilà. Alors, a beautiful thing that Johan LERAY proved just after his PhD, he settled down all the ingredients in his thesis, and then he had to, one extra rewriting argument just after, is that the properad of double Poisson algebra is causal. And it is the properad, not only the genus 0 graph. I mean, this property relies on acyclicity of some graph complex, and here it's with genus. And for people who have been trying to compute the homology of graph complexes, they know that this is a mess and very difficult. And very recently, 2 weeks ago or something like that, Sergei Merkulov, I should have put the exact reference. He proved at the end of one paper that the infinitesimal bialgebra is not causal, which is a pity because in his paper, he's using this as a model to compute the cohomology with compact support of the moduli space of curves. So it would have been beautiful to have a connection between the two. But there might be something that one can do in this direction. Anyway, so it's very nice. So I said before that we have surjection. You see the picture before, there was no C here. So let me explain what I want to do. So you see here, I'm saying this is biggest space of operations and then smaller and smaller. But there is a way to cheat or a trick, let's say. If you had a curvature, so if you've ever heard of that, what is a curved Lie algebra? It's a Lie algebra equipped with one element, okay, which controls the failure for d to square to 0. d0 is the bracket with that element. So the curvature plays a key role, for instance, in symplectic topology and in many other domains. You can consider a curved version of what I've just said. So you consider curved associative algebra. Okay, again, d does not square to 0, but it's the bracket with that curved element. And if you pass to this level, you consider curved version and homotopy curved version. The epimorphisms I showed you above then become isomorphism, which somehow tells you that the difference between these three notions is quite tiny. Okay, I will explain that more later. Okay, but the bright point is that here, when you have curved pre-Calabi algebras, and you look at it is some Maurer-Cartan element in some higher Hochschild complex. So this gives you one version of derived non-commutative geometry. And this is another way to produce derived non-commutative geometry. And this statement, with Johan, we proved this isomorphic to that. And this was refined by Alexandre Quenet on this. But the result we have with Johan, that this, and that was our motivation, that this is isomorphic to that, says exactly that the two definitions of derived non-commutative Poisson geometry, they're equivalent, which is something that you were expecting from the theory. Okay, so good. So now in the last 10, 15 minutes, 13 minutes, say, maybe you want to know more about the shape of the operations, the higher operations that appear. So what is a homotopy, blah, 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 either V, infinitesimal bialgebra, or double Poisson algebra. What's that? Well, I would like to hide, but I cannot. So if you restrict yourself to guy of one output is you should find a infinity algebra. So one output, you should have some kind of corolla, okay? Yeah, but now we have to accommodate the big double bracket. So now you see an associative product is a binary product. An A infinity algebra has many more inputs. Then what is a homotopy? What is a homotopy double bracket? You're adding a certain number of input and certain number of outputs. So a homotopy blah 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 is made up of operations like this. You have m outputs, and for each number of outputs, you have a certain number of inputs. Okay, and imagine that this is in the plane. Okay, this is planar. Okay, again, if m is equal to 1, you get a infinity algebra. The degree, the blah 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 blah, you don't care. Okay, and then the theory. You can try to find that by hand. It's a nice. Well, I don't know if it's a nice exercise. Ask that to your students. You say, look, I just followed a talk online. There is a new notion called double Poisson, associative product, double bracket. Okay, take this on a chain complex and pass it to a homotopy retract. What kind of higher guy are going to appear? Oh, you're going to find the A infinity structure, but what about the other operations? Well, this is not how we found it. We stupidly applied the causal duality theory for properad, which is quite powerful. So they have to be cyclic symmetric. You can take this bit and put it at the end at the cost of a sign. Okay. You have a certain quadratic relation, which is you take d of this. So this is a derivative. This is a homotopy for a certain relation, which is this. Bon, blah, 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 blah. Just keep in mind that you take two types of boxes, and then you're going to compose them in some way. So here they are composed along, you see one string here, and this is just above and below. Okay, so they're composed actually just at one point. Okay, you have just one output of the first one that goes into one input of the other one, and then you reshuffle the inputs. Okay, this is an awful picture. This is a very pro-paradig picture which does not take into account the cyclicity. So this is quite bad somehow. Um, so there is another better way of rephrase this. So it's a third definition after Traylor, Zenayan, Kontsevich, Takeda, Vlasopoulos. This was found by Paul Seidel. He said, look, I know what I can do. I take a cyclic curved infinity algebra structure on A plus A star, where on A star it is 0. Okay, so what do we do? So instead of considering boxes that are cyclic skew symmetric, like a ribbon like this, or a bracelet that you turn around, you write them in a cyclic way. So this is kind of pictures that you find in Kontsevich, Takeda, Vlasopoulos. You already write them in a cyclic way, okay? So when you have three inputs A1 into A3, you put them like this. Then you put your output. I don't know, in which way do I want to read it? I think I want to read, yeah, wait, this is the problem. So I'm reading it clockwise. First the output, then the input, but in the other way around. Second output, then the inputs in the other way around, etc. And this is very cyclic. Now, if I turn around up to sign, it works. So I like to call them roundabouts, because when we drive cars, we have roundabouts and we enter and we leave the roundabout. Okay, that's it. It admits some quadratic relation. So this is the relation I depicted here. This relation, now written in terms of roundabout, is exactly that. D of this operation is the sum where you take your roundabout and you add an arc. Okay, and when you add an arc, you interpret and you have a colored arc. So where you have an arc, it colors, you partition your roundabout into two zones, one in white, one in gray, and you want to view a certain gradient vector from the white part to gray part, which means what? It means that this is, now you can read, this is one roundabout, this is another roundabout, and this is one output of the first roundabout to the other one, which is this picture. Okay? So that's it. So you see, this weird and complicated thing that you had here is simply partition of roundabouts into two, period. Okay? Now you can tell me, okay, but you said that you have more operations here, more here, more here. Okay. So when we want, so this was curved, curved version. For curved version, I have no restriction except that the number of outputs had to be at least one. Now, if you want pre-Calabi or V infinity algebras, you need at least two inputs when V is equal to one. Okay, you need at least, you have to begin with your associative product. When you look at homotopy infinitesimal bialgebras, you need to ask that you have at least one input. And when you're doing homotopy double Poisson, you need to add more, that each guys here have at least one element, which was not the case for the previous. But anyway, this is the difference between the three notions. Okay, so now to finish, are these notions good? Can we do what we know how to do with A infinity expressions? Yeah, we can. Wow, no. Yes, we can. That's what I just said here in terms of pro-paradig calculus, but let me hide that under the rug. Okay, so again, each of these definitions, they admit a deformation theoretical interpretations. There is a de Giulio algebra which controls them. That is, each of these structures are a Moore-Cartan element in some, now it's higher Orchid complex. Now, maybe what you want to do is, okay, how do I make work infini-morphisms, homotopy transfer? So now it's the end and it's online, so you might be tired. Let me just show you pictures. Just a comic, just a movie. So what are infinity-morphisms? Infinity-morphisms are collections of maps labeled by lambda 1, lambda 2, lambda n to m, okay? And they have to satisfy what? Either you partition your roundabout like this with the gray zone in between and white zone. You view the white zone as your morphism. F, 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 F. So you see, that was what we were doing for A infinity structures. We were doing first a bunch of F and then the structure. That's exactly what we're doing here. Or you do things the other way around. You take always partition, but now you take the dual colors. You put white in the middle, that is first operation, and gray, second level of operation. You do first mu, and then you saturate with F. That's it. So it works very well. It's not too complicated, not too scary, I hope. How do you compose infinity-morphisms? Now you take your roundabout and you bipartition it. Okay, you take partitions, but into two colors, white, gray, white, gray, white, gray. And now you interpret the white as the first maps, which have output, 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 and they compose into gray, and gray have output. That's it. And this is associative because it's this combinatorics behind. I mean, this is a nice way to prove it. Voilà. And all we said before also holds. Well, it needs to be proved, and the methods are not the same, so it needs to be, but it's the end, so just accept that we can do homotopy transfer theorem for all these homotopy bialgebras now, okay? We have explicit formulas, so let me give you the explicit formula for the transferred V infinity, infinitesimal homotopy bialgebra, or double Poisson homotopy. What is the transferred structure? You take your roundabouts and you take the sum of all the partitions, okay? How do you interpret that? You interpret that as you have some first zones, so where you apply the first operation. So for instance, you might have this, that, and then when you pass from one zone to another, the arrow H is your contracting homotopy. You remember before, for the trees, we were labeling the edges with the contracting homotopy. So under the bijection, roundabout, and vertical composition of maps, it's exactly that, okay? So this roundabout can be read as follows. It is a bunch of maps, so a box, okay, with inputs and outputs. All the inputs are labeled by I. All the outputs are labeled by P. That's it. And when you go from one zone to another, you pass from one to another. I should have written an arrow down. You label by the contracting homotopy. And it works. And the way we proved it, this is maybe what I prefer with this, is that we didn't start from the formula and prove that it worked. We knew we knew that the theory was working. We knew that we had some conceptual formula, and we made it explicit. So we never checked that this is homotopy double Poisson structure. We know it. This is the real power of operatic calculus, okay, properatic calculus. And then everything works well. Infinity quasi-iso can be invertible, and this is the beautiful guy. Ah, okay, now you see 25. We are trying to finish a version now. This works. You can use it. We have the proof for 3 years, maybe 4 years. Okay, anyway. There exists a zigzag of quasi-iso of double Poisson algebras if and only if there exists an infinity quasi-iso. And this opened the doors to the formality theorem. So let me tell you what is formality. Formality is when you have a zigzag of quasi-iso from a certain double algebra, double Poisson algebra, to its homology with the trivial and stupid structure. You know, I'm back to the first point of the talk. When we had an associative structure and the naively transported associative structure. I said it's bad. Okay. We say A is formal when there exists such a zigzag. It's complicated. You have to build intermediate guys. Here, I have no intermediate space that I'm building. I'm just assignments, maps. There is a paradigm shift going from left to right. Here, you need to construct intermediate spaces. Okay. Here, no. You just have to give more mappings. Okay. So you interpret the things exactly the same way. You have an homotopy transferred P infinity structure on A. These are usually these higher massy products. Okay, I'm going very short. And if this transferred structure is non-zero, then it cannot be formal. So these are obstructions to formality, okay? But for a very long time, we know they are non-faithful obstructions, okay? So, okay, I compute massy products, and they're zero. Does it mean that it is formal? No. They have to vanish in a uniform way. Ah, shit, yes. But very recently, Colin Emprunt, she studied what is called Caledine class, but Caledine class work only for A infinity, or they were developed only for A infinity algebra by Caledine. There were some works by Melanie and Rubio for binary quadratic operas with some restrictions. And Colleen completely extended that. So she developed faithful obstructions to formality. So you might love that because she comes and she says, compute that class. She gives you one class, okay? So, and if that class is zero, I mean, that class is zero if and only if your algebra is formal. If and only if. Wow, okay? And the range of application of Colleen theory is amazing. Well, I like that. Of course, I'm biased, it's my PhD student, but the range of application is amazing. She can work with any structure encoded by a colored properad, not necessarily in characteristic zero. So with this new algebraic theory, she was able to prove the formality result in characteristic P, in geometry, algebraic geometry, topology, etc. Wow. Right, this is great and bright improvement of the theory. And let me finish by citing this. Yeah, so this is the last point. So applying this general algebraic theory of faithful obstruction classes that I like to call Caledine emprunt for a certain reason, they've been studying with Alex Takeda, and this is, yeah, it was put in March, so maybe 2 weeks ago. So they said, look, let me look at the spheres. Okay, let me look whether they are rationally coformal. Let me hide that under the rug. The co. Okay. Okay. Are spheres rationally coformal? But not with respect to the cup product. They want to take into account the Poincaré duality for the first time. So they've been considering this pre-Calabi structure on the cochains of the spheres. It turns out that for spheres, for degree reason, the bitensor is zero. But the full pre-Calabi structure still survives. So among the two infinite sequences of higher operations, just one is zero, but the rest remains. For instance, they have a guy with zero input and three outputs, etc., etc. And they prove that it's not only rationally formal, but intrinsically rationally coformal. So it's super strong. Okay, this is maybe the first or the one of the very first formality statement for bi-algebraic structures. Okay, and they've been even further. They prove that in characteristic zero, this is wrong. You cannot have coformality of spheres in characteristic zero. So that's it. Thank you very much. And please, if you have questions, I would be very happy to answer.
Thank you, Bruno. Very nice talk. Questions?
Please.
I had the question, do you have good classes of formal double Poisson algebras or formal infinitesimal bialgebras or formal V algebras?
What do you mean by formal?
Yeah,
In terms of
formal in the sense
formality,
of...
ouais. Alors, I mean, you want DG double Poisson algebras, which are, well, wait, which are formal. Yeah, there is a. Alors, non, but I think one can get from you take the Kobar construction. Give me 1 second. Yeah, you take the Kobar construction of some coalgebras with a pairing. Then if you do that using the pairing, you do Kobar of coalgebra with a pairing. And if you do that, you get a necklace double Poisson structure, and this has good chance to be formal. This is something that should be checked, for instance, with these methods. I don't have the. I'm very sorry for the authors of this paper that define this necklace, blah blah blah, etc. They've never proved the formality, but I can send it to you, Friedrich. So this is definitely a very interesting class of. I don't want to say I conjecture they're formal because I didn't do the computation, but it feels. You see, for instance, you start from a Kosul coalgebra, which means that the Kobar is formal. With this pairing, it has great chances to be formal in this higher setting. So Yeah, so nobody ever did. I told that to Colin, she didn't want to do it. But there's definitely this. Yes, this could be a good example of, and not that complicated. But I don't know the amount of computations. It's
Okay,
nice
thank you.
to study. Any other
More
questions?
Yes, I have a question as well. So thank you first for the very nice talk. And just for my knowledge, so in what you explained, where do these double quasi-Poisson algebra, where do they sit in there?
Alors, attends, double quasi-Poisson. Alors, I don't know. Alors, sorry. Alors, double quasi-Poisson. Alors, they should be related to the double Poisson. Alors, attends, I'm sorry.
So, because if I remember
Yeah.
correctly, there is a result of Fernandez and Erskovich who say that there are also examples of pre-Calabi, but I don't know if it's helpful or
Alors,
not.
yeah, alors, I've been quick, so and you should go to Maxim's homepage because he's the best expert on double Poisson algebra that I know. It is true that this statement that I said here, we're not the first one to study that. So I should mention Erskovich, Fernandez, Yudu, Kontsevich, etc. But what they have is partial. They have results, but their notion is not homotopy stable. So notion of quasi-Poisson, Pridham also has something. This is definitely a good all notions are good. But this one, I know which property it has. Homotopy transfer, invertibility of infinity morphism, etc. The other ones, I would say they are partial results. They are still quotient of something. I mean, if you think in terms of opérades, you see, these guys are encoded by quasi-free propérades. Okay, so, and their notion, as far as I remember, but this is explained in the paper with Johan, and Johan is better expert than me about this. What I remember is in this quasi-double Poisson that they have, things are free, but there are still relations. So there is still mode out quotient by a properadic ideal, which means that this is ill-behaved with respect to homotopy. It's not homotopy stable. So I would say this is the ultimate result. You see where exactly you have the good, you have to relax everything up to homotopy.
Okay, well, thank you for the answer, and it was a really, really nice talk for me to
Sorry,
understand what's happening here.
Thank you very much. Go and look in the paper with Johan. He wrote things about. We tried to be to acknowledge the literature well enough, and there are some parts where we explain. We say, okay, to compare with this notion of, here is how it works. If you don't find, send me an email, and I will tell you where to look at, and we can discuss that more if you need.
Okay, perfect. Thank you very much.
Thank you. Does anyone have any questions?
Doesn't seem.
So if there are no questions, once again, thank you to our speaker for very impressive and interesting talk. And see you on next Monday in next seminar. Thank you.
Thank you very much for the invitation.
Thank you.
Bye-bye.
Bye.